Hello, this is Mr. McGovern, and this is the first video in the Unbalanced Forces series, where we're looking at the formula F equals ma, also known as Newton's second law, and how that applies to what we've learned so far about unbalanced forces. So we'll start with a simulation. We'll talk about Newton's second law and how it works with calculations and with vectors. So here I've got a simulation on the PhET program. You can go and check it out if you want. There's a cart in the middle, and I can add a small person to the left side, applying a force, and a large person to the right side, applying a larger force. So you can see that with these two forces, the total force is going to be to the right side. So you expect the cart to move to the right side as well. But the key point here is that net forces don't just cause movement, net forces cause acceleration. You can see that speed increasing towards the right as it goes on. So it's really important. Net forces causes accelerations, not just movement. Okay, so here I've got the guy and who can push this little cart. The same thing. I'm going to push it with about 100 newtons, and you can see the speed of the cart increasing. Once again, net forces cause accelerations. They don't just cause movement. And you can see the rate that acceleration is happening. You can see how fast that speed's going up. I wanted you to see that because I'm going to do it again, but instead of the 50 kg block here, I'm going to take that off and put on instead a 200 kg fridge and try and push it with the same about 100 newtons. And so you can see again, even with the heavier object, it still accelerates. However, its speed is changing much slower, so its acceleration is lower. So a net force in this case still causes an acceleration, but with a larger force, it causes a smaller acceleration. So we can put those two ideas, that a net force causes acceleration, and that the larger the force, larger the mass, the smaller the acceleration, together in one formula, and that formula is F equals ma. Now I don't like that because it's technically not correct. The way it should be written is sigma. That first letter there is a sigma, which means total in physics. So it looks like a capital E, and it reads total force is equal to mass times acceleration. I also don't quite like that either. The way I like to write it is to rearrange it. So I divide both sides by mass, and I get that the acceleration of an object is caused by the net force on that object divided by the mass. So when we write it this way, we have a cause side, the net force on the object with its mass, and the effect is the acceleration. Now when you write it like this, it's also very clear to see that when we had a larger mass, we had a smaller acceleration. This is an inverse relationship between acceleration and mass. The bigger the mass, the smaller the acceleration. The smaller the mass, like the little box, the larger the acceleration. So this formula, Newton's second law, F equals ma, or how I like writing it, acceleration is total force over mass, can be used for calculations. And often that's all it's used for. You know, you get given numbers and you can calculate something. However, just as important, it's also a vector formula. Now remember, vectors are things that have direction. So we could talk about velocity, say, being 20 meters a second, but positive, so it's moving in the positive direction. Or we could say velocity is negative 20 meters a second, it moves in the negative direction. Right? So vectors have direction. Now in that formula, mass doesn't have direction. You can just have 100 kgs or 50 kgs. You don't have positive or negative. But force and acceleration both have direction, and the formula says that they both have the same direction because they're equal to each other on either side of the equation. And it's a really important part of this that often gets missed in classrooms, is that the direction of the total force on an object is also the direction of its acceleration. So we'll look at another video that shows that in the same simulation. So here I have my guy applying a force to the right. The cart accelerates to the right. You can see it doing that. So what I can do is I can take that force down slowly to zero and starts moving at a constant speed. And then if I apply a total force to the left, even though the cart's still moving to the right, it's accelerating to the left because it's slowing down. It's still accelerating to the left because it's slowing down, still accelerating to the left. Eventually when the speed reaches zero and I hold that force there, it's still going to keep accelerating to the left, but it will start speeding up to the left. Okay? So nothing's changed with my total force, pushing to the left side. But you saw two different cases there. One in which it slowed it down, that was still accelerating to the left and one at which it's sped up, still accelerating to the left. So the summary here is two things. The formula F equals ma is, in terms of if you want to understand physics, it's better to write it like this. Definitely you need the sigma, which is that funny Greek letter that looks like a capital E, which means total force. But also I like writing it so we've got accelerations caused by the total force divided by the mass. And the second part of this equation is it's a vector equation, which means that the direction of the total force is also the direction of the acceleration always.